Looking at question 9, a system consists of an ice cube placed in a cup of water. The system is thermally insulated from its surroundings. The water is originally at 20 degrees Celsius. Which graph best shows the variation of the total internal energy of the system with time? Now, because it says that the system is thermally insulated from its surroundings, the total internal energy, now the total internal energy, the U, is actually made up of two things. It's made up of the potential energy of the particles and the kinetic energy, the Ke. This comes from the bonding, the strength of the bonding. So that comes from the bonding, and this comes from the movement of the particles. So this total U, therefore, would be the same because it's thermally insulated. So no energy is coming in or out. So it would be A. Alright, going on to question 10. It says here, thermal energy is added at a constant rate. That's an important word. Constant rate to a substance which is solid at time t is equal to 0. The graph shows the variation with time t of the temperature T. Now, we're actually going to be using these two formulas over here. This is the thermal physics section, so we need to be thinking of these three formulas, but this is dealing with when you have a temperature change, when temperature is changing, so you get a change in temperature, and this is when you're having a change of phase. So this over here is the specific latent heat. It's the amount of energy needed to change the phase of a substance, 1 kilogram of a phase of a substance. And this is here is your specific heat capacity. That's the energy required to raise the temperature of 1 kilogram of a substance by 1 degree Celsius. So in this section over here, that section over there, so excuse the line, this is where Q is equal to mc delta T would apply, and these over here are where you're having your phase change. This is when your Q is equal to ml, and again here's Q is equal to ml, and here this one over here. So when there's a temperature change taking place, we're using this, and where there's a phase change, you can see here that when there's a phase change taking place, there's actually no temperature change taking place there. So let's look at the question a little bit in more detail. Which of the statements are correct? The specific latent heat of fusion is greater than the specific latent heat of vaporization. Now, is that true or false? Let's just clear it so we can see what we're doing here. Alright, so this is the fusion part over here. This is when it is melting, because it tells us that we start off, the graph shows, it says, which is solid. So we go here, so here's where it's melting, and here's where it is vaporizing, it's turning to vapor. Now, because the heat is added at a constant rate, we can see that we need a lot more heat here. This Q, if we call this Q2 and this Q1, Q2 is much greater than Q1, because you needed a lot more time to get the correct amount of heat. So if we have a look here, you've got the same amount of mass, therefore your L here for the vaporization must be much greater. So 1 is actually false. For 2, the specific heat capacity of the solid is less than the specific heat capacity of the liquid. Basically that means is that for the same amount of heat, the temperature will rise more, because your specific heat capacity is the energy required to raise the temperature of 1 kilogram by 1 degree Celsius. So if it's rising quickly, it means that it's the same mass in each case. It means that the temperature is rising quicker, therefore the specific heat capacity is actually lower. It's taking less heat, it takes less heat to raise it by 1 degree Celsius. So in actual fact, this is correct. This for the solid is less than for a liquid. So it's only 2, so it's only 2 only, so it's C. Going on to this over here, now this is, you need to learn the kinetic model of ideal gases. Which of the following assumption made in the kinetic is an assumption made in the kinetic model of ideal gases? Molecules have zero mass. That's not true. The forces between the molecules are attractive. That's not true. It actually says that there are no force between the molecules except when they collide, and then they are repulsive. So that's not true. Collisions between molecules are elastic. This is true. And molecules move at high speeds. Not always. They can, but they can also move slowly. So 11C is the correct answer there. Okay, now we're going on to the waves section here. So let's move on to this, the next sheet in our data booklet where we deals with waves. Okay, so it says the object at the end of a spring oscillates vertically with simple harmonic motion. The graph shows the variation with time of the displacement x. The amplitude is x0 and the period of oscillation is t. Now, usually when we have x, we've actually got these two formulas here. Now, it all depends on the starting position. If it starts when you're at t is equal to 0, x is equal to 0. If you start at your equilibrium position, then you use this graph. If you start when you are at your maximum displacement at your x0 position, then we use that. And obviously we're using this formula over here because we actually got a cosine graph here. We're starting at we're not starting at 0, but you can see it's minus, so it must be this one over here, minus the cosine of 2 pi. And this 2 pi t, obviously you realize was from that formula over here. Omega is equal to 2 pi t. Remember also that t, which is a period, is equal to 1 over f, and so we can write that omega is equal to 2 pi f. Down to the next question here. Which of the following is the correct expression for the maximum acceleration of the object? Okay, so now our formula for the acceleration is not given in our data booklet, but you really need to remember this formula. It's your definition of simple harmonic motion, is that the acceleration is equal to minus omega squared x. So this occurs at its maximum when you're at x0. So it's this one over here. So we are going to have omega. Omega we know from this formula over here is equal to, so omega squared is going to equal 4 pi squared over t squared. So we put it in here, so we're going to get this formula over here. It would be 13c. Alright, good. Going on to the next one here. It says one end of a horizontal string is fixed to a wall. A transverse pulse moves along the string as shown. Which of the following statements are correct for the reflected pulse compared to the forward pulse? One, it moves more slowly. Generally it will move at the same speed. That depends on the tension. Usually the tension and the material that's going through. That gives an idea of the. it has less energy. That could well be the case. I mean, there could well be energy lost there where it interacts with the wall, so that's quite possible, yes. And it is inverted. When it comes back, it will be like this, although not that shape. It will have a similar shape like that. So it is 2 and 3 only, so it is C, 14C. Monochromatic light travels from air into water. Which of the following describes the changes in wavelength and speed? Okay, so when it goes from air to water, it actually slows down. The refractive index of air is equal to 1, and for water, H2O, well, I'm not quite sure how much it is exactly, but it's about 1.5. So if we take this formula over here, this is our formula here, we have, if we have Na over N water, I wonder if we should do it the other way around. Well, no, let's do it like that. That would equal the velocity in water over the velocity in air. Now, therefore, I am going to have my velocity in air is going to be my NW VW over NA. So because this is 1, this is actually going to be the VA is about 1.5 times that of the velocity in water. So when it passes into another medium, the light actually slows down. So the speed decreases. So we either here or here, one of these two. Now what about the wavelength? Now because your velocity is equal to frequency times wavelength. Now what's important to remember is that the frequency doesn't change. This doesn't change here. It doesn't change. So therefore the lambda must change, but it's directly proportional. So if your velocity is decreasing, your lambda must also decrease. So the answer is going to be D over here. Both of them decrease.